neural network where we have an m-sized vector with their corresponding weights, and we multiply them with their weights and then add them. And so z is here. It's basically a linear combination of them. And then we send this to an activation function, example ReLU. And the output of this activation function is our target value. So let's come to feed-forward network. Here again, we have an m-sized vector, but instead of having just one z value, we have multiple z values. Here we have n z values, and then again we send their output to their corresponding activation functions, and the output of those activation functions are our target values. So here we have n target values. Any questions so far? Coming to CNN's, convolutional neural network. So here we have an input of size 5 by 5, and we have a sliding window of size 3 by 3, which is the same size as our filter, which is 3 by 3. Then we do an element-wise multiplication here, and we sum up all the values. So let's see how we got minus 74 here. So we multiply minus 1 with 21, then minus 1 by 19, and so on and so forth. And then we add all those values, and the resulting value is minus 74. So this is a very common architecture of how, way of how CNNs are used in practice. So if you have, let's say, if you want to classify MNIST digits 0 to 9, so you can, or if you want to classify everyday objects, then you can do so using this architecture, and the classification accuracy is pretty good. I won't go into the details of this architecture, but you can, find it online. So coming to the basics of graphs, I'll talk about graphs here, and then we'll discuss about GNNs. So here we have a vertex, also called a node, and this is an edge, also called a link. So two nodes are connected by an edge, right? That's all there is pretty much to it. So there are two types of graphs, undirected and directed. So in an undirected graph, there is no restriction as to how you can travel from one node to the other. So let's take two nodes for here, like 1 and 2. So you can travel from node 1 to node 2, and then again from node 2 to node 1 without any restrictions. But that's not the case in a directed graph, because in directed graph, here the edges, the edges from node 1 to node 2. So you can only go from node 1 to node 2, but not from node 2 to node 1. That's not possible. So now let's talk about adjacency. Right. So now let's talk about adjacency matrices. So we have three types of graphs: undirected, directed, and weighted. And we have their corresponding adjacency matrices. So now let's see how we create the adjacency matrix of an undirected graph. So since node A and node B are both connected by an edge, so we see the row of A, and we see the under the column B, we have 1 here. That means that there is an edge present that is connecting node A to node B. Now in row B, under column A, there is again a 1 present, which also indicates that there is an edge present between nodes A and B. Now let's come to the adjacency matrix of a directed graph. So here you can see that the edges from node A to node B. When you look at the row of A under column B, there is 1 present. However, when you look at the row of B under column A, there is 0. This indicates that the edges from node A to node B, but not from node B to node A, right? So that's the restriction here. And the adjacency matrix of a weighted graph is very similar to how we get the adjacency matrix of that of an undirected graph. The only difference is that instead of putting 1 here, we just put the weight of weight on that edge. So there is an edge present here with a weight of 5. So we put 5 here and here instead of 1. That's the only difference. Any questions so far? Okay, so there are three areas, there are 3 ways where you can use GNNs. There are many more, but I'll discuss here 3 only. So first is graph classification, wherein you have to predict the whole graph. Like you have to predict what a particular graph is. An example could be like, you have a structure of a molecule, and you want to predict, okay, so what's a particular molecule, right? And the second area is node classification, where you have to predict nodes. Like, for example, if you take social networks, then maybe you want to predict. Okay, so depending on who's your connection, who might your friends be, whom you might likely know, and all those things. And finally, link prediction. In link prediction, what we do is we try to predict the missing links. So if you take again molecules, then in molecules you might you might want to predict, okay, if there is a particular bond between two atoms or not, or two molecules or not, so on and so forth. Right.
So is the link and edge inside the graph, or is it?
What do you mean inside the graph?
So in the graph, would the link be an edge?
Yeah, link is also called an edge. Node is also called a vertex. Does that answer your question?
Is graph classification the same as the combination of node classification and link prediction, or what's the difference between combining the second two and the first one?
So for graph classification, you have to predict the entire graph. But for node classification, you have to predict only like certain amount of nodes or just one node. And for link prediction, you have to predict missing links.
So it's like combining the nodes.
Those are different problems.
I think you can say that in some way it's similar to
But not entirely. Did I answer your question?
Yeah, so basically you have to approach it in a different way once you try to do both.
Kind of, yeah. But you can look at like, PyTorch, Geometric and other libraries. There you can find, the code of these things. And that I think might clear your answer better.
It's not very fun. It's just endless. Probably this whole human. It's just
even something basic like give a molecule and you want the project is acetic basic or neutral. So you have three classes, and then you want to assign each molecule to the particular class. So
Okay. So in that case, it would be like classifying the entire graph as opposed to like generating the graph.
yeah, this is not generation, this is just classification.
Oh, okay. That makes sense.
Right. Now let's talk about node and edge embeddings. So both nodes and edges, they have their own features, or you can call them embeddings. So here, like say we have vertex A or node A, and this is an embedding. Like this is just, a dummy diagram of how an embedding might look like. It's basically a vector. And similarly, an edge also has its own embedding. So this is the diagram of an edge embedding, which is again a vector only. But the question is, why do we need node embeddings? Anyone? The answer is very simple, because we want to be better able to represent the information contained in them. So my question is, how do we pre-process words before feeding them to a neural network? This is kind of an analogy here. So if you've done natural language processing, you might be, you might know about the answer about this. So anyone knows the answer? Yeah, right. That's the answer. So answer is word embeddings. And so this is a diagram of word embeddings. And you might relate this diagram as when I talk about node embeddings or edge embeddings. So, you might think, okay, you might keep this diagram in mind as here, different columns represent different things. And say, for example, we take man. So man is a living being. So we assign a score of 0.6. But man is not feline. So we assign minus 0.2 because man is not feline. So this is the idea of word embeddings or node or edges embeddings. Any questions so far? Yeah.
Was this taken your attention? So when you
Yeah. Right. Now let's talk about the equation of a linear layer. So this is a vectorized equation of a linear layer. When I talk about perceptron, this is what we were doing there. So Y here is the output matrix, X is the input matrix, and W is the weights matrix. So now, since we are dealing with graphs, we will need a way to incorporate information about how each node is connected. Right now, this is just an equation of a linear layer. But how do we convert it or modify this equation to that of a graph linear layer? So we will make use of adjacency matrices. And The reason is, first, because an adjacency matrix contains the connections between every node in the graph. And by multiplying the input matrix by this adjacency matrix, we will directly sum up the neighboring node features. And the second reason is we can add self loop to the adjacency matrix so that the central node or node in consideration, I think node in consideration, I'll make this clear in the upcoming slides. And so, the central node is also considered in this operation. And if you want to know what self loops are, so this is a self loop. So this means now node A can go from, if you're at node A, you can either stay at node A, go to node B or node C. So this arrow over here is that of a self loop. Right. So to include self loops in our adjacency matrix, we just add the identity matrix over here, which is the same size as that of the adjacency matrix. And this is the updated adjacency matrix equation. So initially our linear equation was this. Now we modify it and write, we just pre-multiply by the adjacency matrix, the updated adjacency matrix. And so this is the updated equation, and this equation represents the equation of a graph linear layer. Any questions? Yeah.
So in this case, what does X actually represent? So
Node
these are like
embeddings.
The nodes are essentially like vectors, right? So I'm guessing in this case, the size of X has to be in the same dimension as I suppose, like. But then let's say like we want to include like more features in our vector, like embedding. How do we?
You do that initially, not
So
afterwards.
actually, X is of the size n times C, where n is the number of nodes and C is the number of features for each node.
Okay.
This is
the
a
weight matrix is adjusted in terms of C times.
okay. So now let's generalize what we've been doing so far. And so the idea behind the graph linear layer was to take the linear combination of features from the neighboring nodes, including the target node or the node in consideration, with the weight matrix, and then take the sum of this. So we can generalize the above using a message passing neural network framework. Essentially, there are just 3 steps in it. So first, I'll explain a gist of these three steps, and then I'll explain them in detail in the upcoming slides. So in the first step, each node creates a message for its neighbors. And afterwards, each node aggregates the messages that it received from its neighboring nodes. And finally, the node's features are updated using the aggregated messages. So every node uses a function to create a message for each of its neighbors. The message can simply consist of its own features or also consider the neighboring node's features and the edge features. Then every node uses a permutation equivariant function, for example, concatenation, to aggregate the messages from its neighboring nodes. A function is said to be permutation equivariant if you say permute the inputs, then the output also gets permuted in the same way. So let's take f of x comma y, and f here is a concatenation function. So if you here you have concatenated x and y, but if you permute, let's say instead of sending x comma y, you send y comma x, then the output also gets permuted in the same way. So this is a permutation equivariant function. And then in the update step, the final step, every node uses a function to update its features by combining the current features and the aggregated messages. So for example, a self loop can be used to update a node's features by combining the node's current features and the aggregated messages. So now I'll give an example of what I've been talking about. So I think that will make more clear. Okay, so let's first, talk about some notation. So h sub I here is the node embedding of node I. H sub j is the node embedding of node j. E sub j comma I is the edge embedding of the edge from j to I. And h prime sub I is the updated node embedding of node I. So for the first step, suppose node I creates a message using its own node features and the features of node j and the edge features of the edge between nodes I and j. using a message function. This message function can be anything, like you can take an average, anything, right? So this function is our message function. So this was just one message. Node I creates one message for each of its neighboring nodes. So let's denote the set of node i's neighbors by n sub I. Okay, so now suppose that node I created and received one message from each of its neighboring nodes. So node I aggregates all the messages it received from its neighbors along with its own features using an aggregate function. So here we iterate over the set of all node i's neighbors here. And this is the message function wherein node I received all the messages from its neighbors and also created the messages. And in the final step, node I updates its features by combining its current features and the aggregated messages using an update function gamma. So here, first node I created the messages and received it, and then aggregated all those messages using this function, aggregate function, where we iterate over the set of all neighbors of node I. And finally, it updates its own features, the embedding of node I, with all the aggregated messages here using a gamma function, which is our update function. And this here, I prime sub h prime sub I is our final updated node embedding of node I. So this is the whole equation with all the variables. Any questions so far?
Unless if you combine its own features, does the aggregate in order to get something?
Yeah. Node I's own features as well as all the aggregated messages that it received from its neighbors.
And the aggregate doesn't contain the features of the node.
No, this is a function. The features are created or received using this function. Phi.
What else could the aggregate function be from an intuitive perspective?
So I talked about concatenation as one example. Can you think of something else? A permutation equivariant function, meaning if you permute the inputs, the outputs also should permute in the same way. An example?
I think concatenation is the most complicated. That's what makes most sense.
Is it like mostly the most common one used in this?
Any more questions?
So now we'll talk about a specific problem where we'll use a specific type of GNN to solve it. So let's understand the problem first. So the problem we have here is of a citation network. So what a citation network is basically, it's a graph where each of the nodes represent different documents, or you can think research papers here. And if there's a node which goes from A to B, you can think that A cites B and so on. And such a network finds uses in like search tools where you want to find similar papers to your work, or you want to read similar papers, something. And it has also been used in legal judgments where you want to see which other cases have cited a similar case and so on. And it can also help in some citation analysis stuff as well. Now the problem here is, let's say we are given one such database, let's say of 1,000 archive papers or so, and only a part of them are sorted into different subject headings. Let's say paper A belongs to the computer vision category, paper B belongs to NLP category, paper D belongs to audio category, but all the other nodes are not classified directly for us. What we want to do is we want to use the information from the nodes which are classified and the citation network to kind of guess what the other nodes could be classified as. Now, before we delve into solving the problem itself, I'd like to go on a detour and discuss some mathematical foundations which would be useful to understand this. So first, we'll start with convolution. So you can consider this f, which is given here, which you can basically think of as an array of numerical values or a function if you want. And you might have heard about calculating moving averages, where we take a particular window of, let's say, 10, and we place each value in f with an average of the 10 elements around it. So what convolution does is basically we assign some weights to each of these weighted average. Instead of just averaging directly, we say that the elements which are closer to a particular element have more say in what the average should be. And when we do that, we end up with something like this, where let's say this was f, and we use this particular filter g. When we convolve with f with g, what we do is basically we center this peak of g at a particular value of f and multiply, like, you can think of it as similar to the first convolution network which you saw, where we did element-wise multiplication and added up all the elements. That's the same thing which we do, but we take the average in this case. And so this kind of helps in getting more useful features and more useful information, so that each value now not only contains information about itself, but also some more information about its neighbors in a way. And mathematically, it is written in this way, where f star g means f convolved with g. And by the way, this is like commutative, so you can do f convolved with g is same as g convolved with f. And the way it is defined mathematically is basically iterating over all the infinite points, centering g at the current point, and then multiplying element-wise and taking their sum. Is it clear till now? Now let's talk a bit about Fourier transforms. First, I'd like to give a bit more visual understanding. Yep. So what Fourier transforms are basically, let's say you consider this particular wave. Again, you can just think of it as a function or a particular vector of values in a way. And what we want to do is we want to break it up into different sine waves. So for example, this wave over here can be broken up into these two sine waves, which we can just add to get back this value. Now, if you consider a more realistic value, such as this square wave over here, which doesn't have an exact sine representation in a couple of sine waves, but if you take infinitely many sine waves, ultimately you will end up with something which almost exactly approximates this. Now the thing is, like, of course, when you have infinite sine waves, you get the almost perfect representation. But if you decrease the sine waves, you get a slightly imperfect version of the original wave. But it is still pretty good and it's pretty usable. And the reason why we use this is because let's consider this as an audio. So the audio is stored as a stream of points, or basically a vector. And let's say you have a 3-minute audio, it's a lot of values to store. But when you break it into sine waves, and let's say you just take the first 100 sine waves, now for each sine wave can be represented by just two values, which is the frequency and the amplitude. So instead of storing a thousand valued vector, you can just store, if you take 50 sine waves, you can just store two variables each, so 100 variables, and you'll be able to reproduce this wave, not perfectly, but approximately. Right. So that is what a visual understanding of sine waves is. Yep. So what it does is basically, given a vector, it transforms it into a bunch of different vectors, in this case, maybe two or more. And what we call them as being present in the Fourier space. And now they're no longer present in the normal space, because numerically they don't represent values which you can comprehend directly. You need to transform them into some other basis, in this case, sine waves, to convert them into the normal space. And the main use over here for us is basically this convolution theorem, which says that convolving a particular function f with h is the same as taking the Fourier transform of each of them and multiplying them. So this is a pretty famous and very useful result. I'll not delve into the proof of this, but it's not too difficult to prove. Maybe you can see it later online. But this is what we'll make use of here, which says that if you convolve f with h, it's same as taking their Fourier transform and multiplying them. And this also plays in the reverse direction, which means that when you want to convolve Fourier transform of f with Fourier transform of h, it is the same as multiplying in the normal space. Is that clear to everyone, or have any questions? Yep.
So they're basically taking Fourier transform of from F and H.
Yep. Yep.
Sorry, so what were you doing in the previous presentation with the Fourier transform, taking it into sine? What's that related to this?
It's basically the same thing. So instead of having the vector represent values in f and h, now you have a vector f. Now you have a vector capital F, which represents certain coefficients for the sine wave. In this case, amplitude and frequency. Yep. So basically, when you want to do convolution, if you remember, like the mathematical way to do it is you need to iterate over all the points and do a pointwise multiplication for each and every point. So this would be something like n square probably. M log n, okay. But this is pretty fast. It's pretty much linear in a way, I think so. Okay, I'll move on then. So the next topic we need to study about is the graph Laplacian. So let's say you have this particular graph and you already learned about the adjacency matrix A. Let's define another matrix, which is called capital D, or the diagonal matrix, which has the values of the degree of each node on its column. So basically, if you sum up each, so basically it represents the number of connections each node has. So let's say let's consider the second row. It corresponds to node 2, which has a degree of 4 over here, which is why we have a value of 4 here. And the fifth node has 3 edges, which is why the degree matrix has a number 3 over here. And the way we define the graph Laplacian is basically we define it as D minus A. And the reason this is useful is because now it not only contains information about the individual edges, it also contains information about the number of different edges each node has. So in one matrix, you are able to get two kinds of information. Now you might have noticed a potential issue with this. It is that, let's say in this case, node 2 has 4 features and 4 nodes, 4 edges, and node 1 has only 1 edge. So in the graph, in the Laplacian matrix, the edge node 2 will have a lot of weightage when you go on to compute stuff using this matrix later on. So what we want to do is we want to normalize this effect, which is why we define the normalized adjacency matrix, which is basically taking the negative square root of D multiplying with A, and then again multiplying with negative square root of D. Now, what you can think of this as intuitively, basically taking each row and multiplying it and dividing it by the degree of that particular node. So each value in the first row is divided by 1. Each value in the second row is divided by 4. So basically, you normalize the number of connections each node has. And then we can compute the normalized Laplacian in the same way by basically computing I minus the normalized adjacency matrix. And this is the normalized Laplacian graph matrix. Anyone have any questions? Now our last mathematical topic, which is eigen decomposition. So what this means is basically, let's say you're given this matrix A. What we say is that for certain type of matrices, there exists a set of eigenvalue and eigenvectors where if you multiply A with that vector, you get a scaled version of that vector itself. So in this case, if you consider this to be a matrix, half 1 is an eigenvector, which when multiplied by A gives 4 times itself. So in this case, this would be called an eigenvector, and this would be called an eigenvalue. And eigen decomposition is basically taking a matrix A and dividing it into a set of eigenvectors and eigenvalues. So for this matrix A, the two sets of eigenvectors are this 1 by square root 2, 1 by 1 by square root 2 with an eigenvalue of 3. And another eigenvector is 1 by square root 2, minus 1 by square root 2 with an eigenvalue of 1. And this theorem says that basically if you concatenate the vectors into a matrix, which is the eigenvector matrix, and then you make a diagonal out of the eigenvalues, and then you multiply it in this way, which is u lambda times u transpose, what you get is A again. Now, again, I won't be going into the proof of this, but this is what eigen decomposition does. And the reason why this is important is basically you can think of it as breaking down A into its simpler constituents. So in a way, you can think that A is made up of these eigenvectors and eigenvalues in some way. Does anyone have any questions? Okay, now let's move on to the paper itself. Now the paper is a graph convolutional networks. So let's start by understanding what each layer is, and the layers are called spectral graph convolutions in this case. So we talked about the normalized graph Laplacian matrix, which is defined in this way, which is I minus square root of D times A times square root of D. And what we want to do is basically take the eigen decomposition of this, where U becomes the eigenvector matrix and lambda becomes the eigenvalue matrix of L. Now let's just keep that aside for a bit. Now I'll talk about what we actually want to do in this layer. What we want to do is basically you can think that let's say we assign the subjects a particular scalar. Let's say we assign CV to be 1 and LP to be 2, audio to be 3, and so on, some 40, 50 different subjects. What we can do is we can basically make a signal of size r raised to n, where n is the number of nodes. So you have one scalar value coming from each node, and you can make that into a signal of size n by 1. And for each layer, you will have a set of learnable weights, which again you can think of as being r cross n cross 1, theta over here. And you can convert this set of learnable weights into a filter by taking its diagonal matrix, and it gets into n cross n matrix. And the way these weights and filters are defined is they are defined in the Fourier space. And you'll see why this is important just in a second. And the reason they're important is because what we want to do in this layer is basically we want to convolve X with the filter G. This is important because you want to extract some features, properties, and patterns present in the feature vector X. And once again, we'll make use of the convolution theorem here. Is everyone good till now? Or anyone have any questions? Okay. So we talked about the convolution theorem, where if we want to convolve, in this case, X with G, it basically means taking the Fourier transform of X and multiplying it with Fourier transform of G. Now, since we already defined G and theta in the Fourier domain, we don't need to convert them. So we can just take it directly to be Fourier of X times G. Now, this is a bit of a more mathematical concept, which I'll not be diving into too deep right now. You can search this up by looking for graph Fourier transforms. Now, what it means is basically when you take U, which is the eigenvalue, eigenmatrix vector of L, which we defined over here, the U from here, and you given a particular signal Y. If you want to calculate it in the Fourier space, you can just do U transpose times Y. And when you want to bring it back from the Fourier space to the normal space, you can just do U times Y. Now you can look for a proof for this. It's quite complex to understand, so we'll not be diving into it in this section, but let's just take it as a fact for now. Now this really solves our problem because we wanted to do G theta convolved with X. What we can do is first take X to the Fourier space by doing U transpose times X, and then we just simply multiply it with the filter, which was already defined in the Fourier space. And then we convert it back into the normal space by multiplying all of this with U. So this is how we solve the problem of convolving G theta with X. Anyone have any questions?
So, X here is just,
Right now, you're just thinking of it as getting one feature from each node. So it's n cross 1 matrix. Later on, we'll extend it for C node, C features. Sorry? Okay, yeah. So signal is basically, right now we are defining it as taking one feature from each node. So we get a n cross 1 vector, and filter is basically something we want to apply in this layer. So it's a learnable parameter, which is defined as this diagonal matrix. And again, this is analogous to what we did with the CNN in the first half of the presentation. Okay. So now the issue with this computation is that eigen decomposition is computationally quite expensive. Particularly it's in O of n squared, and we don't really want to do this. So what we will do is we will approximate this. And the way we will do it is again using some pretty advanced optimization techniques, some hand wavy assumptions, and some theorems, which are actually outlined in this paper. Again, we'll not be delving into how exactly we do this approximation, but we make use of Chebyshev polynomials as such, and we are able to approximate this thing into this. It can be somewhat intuitive. You might be able to see that here as well, we have a theta term, we have a x term, and then we have u times u transpose, which is basically represents L in some way. So, and these terms are as well pretty similar to how we defined L. So this is basically a calculatable approximation of that particular term. And this can be calculated in O of n. You don't need to do O of n squared to get this, which is why we make use of this. Anyone have any questions? Okay. Now, again, there are some more issues with this approximation itself. First issue is that there are no self loops in the adjacency matrix. So intuitively, you can think of this as the model doesn't know that each document is related to itself. And another problem is that previously we normalized the Laplacian by doing I minus square root of d times a times square root of d. But now that we do I plus square root of d times a square root of d, it is no longer normalized because d square root of ad basically represents values between 0 to 1. And now that you start adding it to 1, it becomes like 1.5, 1.6. And when you keep multiplying these terms in a neural network, they really start exploding to infinite sizes. And we want to solve this problem. So the way to solve the first problem is similar to what we talked in the first half. We basically manually add self loops to A by creating an A tilde, which is A plus I. And the way we solve the second problem is we use a renormalization trick where we use the A tilde to again normalize A tilde, and we replace IN plus D, D term by the D tilde times A times D tilde, where D tilde is defined the same way as before, but instead of A, now as A tilde. And this gives rise to this term over here. Anyone have any questions? Now, like we talked about, this is in over here, we considered X to be a n cross 1 matrix, n cross 1 vector, where we take just yep. AIG. A matrix is basically A times I, where we basically add self loops to the existing adjacency matrix. And then we normalize it again to form this vector over here. So right now we defined X as taking just one feature from each node, but in reality, we might have, let's say, C features for each node. So we want to vectorize this operation to use matrices now. And the way to do that is basically, if you reorder these terms and take appropriate dimensions, it can be reordered to this, where it is basically the same thing, square root of d tilde times a times square root of d tilde times x times theta, where x is now n cross C matrix with C dimensional features for each node, and n is the number of features, and theta is of the size C cross F, where C is the number of features for each node and F is the number of feature maps. And this is how we get the output Z for each layer in our model. Any questions? Okay. Now that we have defined each layer of the model, now let's define the neural network using these layers. And just a quick refresher on what the problem we were trying to solve. So basically, given a semi-classified citation network, we want to classify the remaining nodes. And the way to do this in this paper was they used a 2-layer graph convolution network, which basically had an input layer, 2 layers, which did the same operation we talked about here, and then an output layer combined with a couple of ReLU and softmax functions. So when you break it down, really what it does is given X, which is an n cross C matrix, and we pass it to the first layer, which basically gives us A hat times X times W0. A hat is basically defined as this term over here, which we were using previously. And then we apply the ReLU activation function. Then we pass this entire thing to the second layer, where it is again pre-multiply with A bar, post-multiply with W. And then finally we pass it through softmax before getting it into the output. And this is how our network is defined. Any questions? Okay, now let's move on to the code implementation.
All right. Now let's focus on the code. So this was the two-layer GCN that we were talking about. But now let's focus on how we will implement one layer, one GCN layer. So this is the NumPy implementation of the neural network on the previous slide. So first we will initialize the weight, bias, the adjacency matrix, and the input matrix here. And this is the forward function. So you need to focus on this equation right here. So this part here, this part is the adjacency matrix, that is A bar, A hat, which is here. And now we use this function, normalized graph Laplacian, and this function, or like, so this is our original adjacency matrix here. And then we send this to normalized graph Laplacian. And so this A bar here is this thing, right? Now we do a dot product. So A bar times X is the dot product, and this is this code here. And then we again do a dot product with that weight matrix, which is here. So NP dot, and this is this. And then finally we add the bias vector. So this was for the forward function. And this backward function here is like, your old back propagation. So any questions so far?
Was there any reason why you guys just use Julia?
That's mentioned in the paper.
So that's what they use in the paper. But you could use any number of variables.
Right. Okay, so now let's talk about how we will implement the GCN, the graph convolution network. So here we initialize the graph convolution layer. Right. So here we initialize the graph convolution layer. Here in feet is the number of input features, and hid feet is the number of output features. Again, hidden layer and output layer both are GCN layers with the respective input and output features. And layers here means number of layers. So the default value is 1. So now let's talk about the forward function. So as you saw in this graph, in this diagram, here first we do a forward function using X and A. Now this forward function, so remember that the init layer is a GCN layer, and when we say dot forward, we actually mean do this, right? So here X and A, and we send X and A here, right? So depending on the number of layers we have, since here we only have one layer as a default value, so we calculate H as follows. So first we use the hidden layer, and again the forward function here, because hidden layer again is a GCN layer. So this forward function over here means this function, right? And we do this to calculate the, so you can see here. So this is so first we calculate H here, and this is the corresponding mathematical notation. And finally, we apply the softmax function over here. So the output of this layer, H, we send this to our output layer. And again, since output layer is our GCN layer, so this dot forward is this function in the GCN layer, the forward function of the GCN layer. And again, this backward function is your old backward propagation. So in practice, you wouldn't just start implementing your own GCN layer from scratch in NumPy. You would use like a library like torch geometric. So in torch geometric, we have a predefined graph convolution layer. So you use this thing. And depending on the number of input features or number of input channels and hidden channels you send here, which is very similar to how you would use a convolution layer in your PyTorch, like simple PyTorch. And the forward function, so first we calculate A bar times X times the weight matrix at layer 0, which is this. Okay, so now anybody knows what edge index is? Any idea? So the shape of edge index is 2 comma num features, where num features is the number of features of X. Why 2 here? So let's take two nodes, for example, node A and B, right? Node A and B are connected by an edge. So what this would mean for edge index is your edge index, an element of edge index would contain like, so it will be a vector of size 2, meaning A comma B, right? And similarly, like depending on the number of nodes and edges you have, you would populate your edge index, correspondingly. So that's what edge index means. And you send X and edge index as the parameters of conv1, which is the first convolution layer, followed by ReLU activation, which is here. And then again, you would apply a second convolution layer as outlined here in the mathematical equation. Finally, you apply log softmax, while log for numerical stability. So this was how you would implement a graph convolution network in PyTorch geometric. Any questions? Pardon? What do you mean type? It's a matrix. Two comma num features. It's the size of edge index. Num features means the number of features of X. Right. So remember that this paper was written in 2017. So these results are, so these models are, like the models used back then. And back then, GCN outperformed all these models. And these here, CiteSeer, Cora, PubMed, NEL, these are all different data sets. So as you can see here, that GCN, yeah.
Oh, I'm just curious, when you were testing for these results, how big were the graphs that I'm talking about? Like, how many edges, how many nodes, or a typical graph that?
These are very popular. If you want more information,
in the paper, right?
So if you want more information about the size, these are all data sets. These are all available in PyTorch geometric. So, just as you would load MNIST or CFAR10 datasets in PyTorch, you can do so, like you can do that with these datasets in PyTorch geometric. And I think that will give you a better idea about the exact size.
Like most of these older models, they have like 10 layers or something. So you can see that the time difference is also pretty substantial for most of the data sets because they did this with just 2 layers. So you can see any introduction.
This is a dataset.
I think it was another node classification. I think it was related to something. Maybe you could check the paper.
Right. So as you can see that GCN outperformed all the the methods used back then with these accuracies. And then these are some innovations. Pardon? That's the inference time, I guess, or training time.
I think it's
Yeah, yeah. Might be.
Over the yes. Not sure, I'll have to check that. Is that stage 1? How do you I don't know specifically. It's maybe
Oh, this is wall clock training time in seconds. This one.
So that's the training time, right?
Yeah. Is that good?
So what's all of these are node classification.
I think the first three are just citation network, the same thing we discussed, and NEL is, I think, something related to.
The solution of NEL, it says never ending language code.
We can just say check the GCN.
It trains in 7 seconds.
Yeah, that's the training time. I think that was for the entire graph, right? It was the training time mentioned. Right. So these are some innovations done in graph neural networks, not GCN, but like specifically. So you can see that initially the accuracy of GCN was around 81%. And then as innovations were done, new architectures are introduced. So now the accuracy has been bumped up to around 91%. So finally, let's discuss where all GCNs are being used. So or GNNs are being used. So GNNs are used to identify existing drugs that would be effective against COVID-19 virus. So platforms like Twitter and Facebook, they use GNNs to analyze user behavior. Again, based on a user's data, they'll help you know, okay, so if you know that person, or if you want to follow that like a particular, somebody else, or do you want to connect with someone, all those things. And companies like Uber Eats and Pinterest, they use GNNs for the recommendation purposes. So, perhaps you might like some Indian food today, tomorrow might be Chinese food, something like that. And Pinterest might recommend you dresses, right? So based on your search history, if based on your browser history, you might like a particular type of dress. And finally, for forecasting tasks, GNNs are used to predict the, let's say, if you enter some destination, how will you get there in the lowest time possible, right? So for all those tasks, GNNs are being used. Right. Any questions?
You know, any specific, I may have asked you this last week, do you know of any specific like viruses and or drug treatments that have been developed using GNNs? Specific, there's one called Allison.
I think also the thing is that most of the pharmaceutical companies probably use GNNs in some way, but then they also have a human in the loop. So they ultimately, maybe they use GNN to accelerate some parts of the process, but overall they would still need a scientist. Or probably don't really just say made by GNN. They do use GNNs.
Does that answer your question?
Yeah.
All right. So that was all for today. Thank you everyone for attending. Again, these slides are available on our GitHub repository. The link is given here. You can, follow us on social media if you want. Next up, we'll have a guest speaker. We'll shortly announce the topic. And later on, we might do a presentation on NERF. So stay tuned. We'll post the announcements on social media.